Hey everyone, Mr. Houck here. In today's video, we're going to be learning about zero matrices, identity matrices, and inverse matrices. Let's go ahead and get started. We're going to begin by looking at zero matrices and identity matrices. Recall that previously we defined a zero matrix as any matrix in which all entries of the matrix are zero. We will indicate a zero matrix with an uppercase O, and we will include a subscript to indicate the dimensions of the zero matrix. For example, if I say O subscript 3 by 2, this means we have a zero matrix that has 3 rows and 2 columns. Or if I say O subscript 2 by 4, we have a zero matrix with 2 rows and 4 columns. Okay, well, it turns out that a zero matrix plays a similar role in matrix operations as the real number 0 would for real number operations. Let's consider the following examples. In the first example, suppose that matrix A has elements 3, -7, 4, and 6. Let's calculate O, the zero matrix that's a 2 by 2, plus A, and 0 times A. Well, let's look at the zero matrix that's a 2 by 2 plus A first. So the 2 by 2 zero matrix would be right here, 0, 0, 0, 0. And we want to add it to matrix A, which is right here. Well, if we go ahead and add them, we know that we add corresponding elements together. So 0 plus 3 would simply be 3. 0 plus -7 would be -7. 0 plus 4 would be 4. And 0 plus 6 would be 6. So notice adding the zero matrix to matrix A just resulted in matrix A again. Very similar to how if we add 0 to a real number, we're just gonna keep the real number. Like 0 plus 5 would be 5, or 0 plus -3/2 would still be -3/2. It works the same way with matrices. If we take a zero matrix and add it to a matrix, we're just gonna keep that matrix the same. Now let's try to take the scalar multiple 0 and multiply it by matrix A. Well, we know that when multiplying a scalar, we just take that scalar and use the distributive property with all the elements of the matrix. So 0 times 3 would give us 0. 0 times -7 would give us 0. 0 times 4 would give us 0. And 0 times 6 would give us 0. So notice that when we take a scalar multiple 0, multiply it to any matrix, we're just going to get a zero matrix in return that has the same dimensions as that matrix A that we multiplied by. Much like how in real numbers, if we take the number 0 and multiply by a number, we're going to get the number 0. Now, with matrices, we can define the opposite or additive inverse of a matrix A as the matrix -A, where A plus -A will equal -A plus A, which will equal a zero matrix of the same dimension of A. Let's see an example. So, suppose, again, let's use the same A matrix with elements 3, -7, 4, and 6. We want to calculate A plus -A equals the zero matrix. So we're saying if A plus -A equals the zero matrix, we want to find -A, which is the additive inverse or the opposite of A. Well, let's see here. Again, we're assuming that A plus -A equals a zero matrix. And let's go ahead and say that -A, we don't know its components yet, but let's say it has A, B, C, and D. Well, if we add A plus -A together, so A being, let me get color blue, here we go. So A is 3, -7, 4, and 6, plus we're saying that the opposite of A, -A, is A, B, C, D. Then this will give us 0, 0, 0, 0. Well, let's go ahead and add the matrices on the left and set them equal to the elements on the right. So 3 plus A will equal 0. -7 plus B will equal 0. 4 plus C will equal 0. And 6 plus D will equal 0. Okay. And solving each of these very simple equations, we get that A equals -3, B equals 7, C equals -4, and D equals -6. So applying that, that means that, sorry, not inverse of A, that means -A, the opposite of A, will equal -3, 7, -4, -6. Now, this is the mathematics behind calculating this opposite of A, but we can just use a lot more common sense. We're really just asking ourselves, what plus 3 would give us 0? Well, 3 plus -3 is 0. What plus -7 gives us 0? Well, 7 plus -7. So essentially, we're just changing the signs here. -3, +7, -4, -6. All the opposite signs create our opposite matrix. Okay, but this is just the math to back it up. So now let's look at identity matrices. We also previously defined an identity matrix as a square matrix with 1s on the main diagonal and 0s for all other entries. Since identity matrices are all square matrices, we can name them as such. So a 2x2 identity matrix we'll call I with a subscript 2. That's just going to be 1, 0, 0, 1. A 3x3 identity matrix we'll call I subscript 3. 1, 0, 0, 0, 1, 0, 0, 0, 1, and so on and so forth. We can have I with a subscript 4 for the 4x4 identity matrix, I with a subscript 5 for the 5x5 identity matrix, and so on and so forth. Now, much like 0, just like the 0 matrix was similar to 0 in the real numbers, the identity matrix plays a very similar role in matrix multiplication as the number 1 plays in real number multiplication. So let's see an example below. In this example, let's take the same matrix from before, matrix A with elements 3, -7, 4, and 6, and let's calculate both the identity matrix, the 2x2 identity matrix times A, and A times the 2x2 identity matrix. Now remember from our video on multiplying matrices that the order that we multiply in is very important, which is why we need to calculate both of these separately. So let's go ahead and calculate this. Let's do this matrix multiplication on the left first. Okay, so we are calculating the 2x2 identity matrix times A, and setting this up, this is what we would get. So we're going to have 1 times 3 plus 0 times -7. That's going to be our first element. Leave a space. Now we're going to have, what did I do there? I messed that up. Be 0 times 4. There we go. Okay, now leave a space. Now we're going to have 1 times -7 plus 6 times 0. So that's 1 times -7, 0 times 6. Okay, then we're going to have 0 times 3 plus 1 times 4. And then we're going to have 0 times -7 plus 1 times 6. All right, simplifying, 1 times 3 plus 0 times 4, that's just going to be 3. From this piece right here, 1 times -7 plus 6 times 0, well, that's going to go away. We're just going to get -7. From this this element right here, 0 times 3 will go away. We just get 4. And then from this entry right here, this piece will go away. We just get 6. And notice that the answer that we get when we multiply the identity matrix times matrix A is matrix A itself. So in that sense, the identity matrix is acting very similarly as 1 would have acted in the real numbers. We know that if we multiply a number by 1 in the real numbers, we just get that number back. Like 1 times 7 is 7, 1 times -0.5 is still -0.5. Well, same here, identity matrix times a matrix A would just be matrix A. And let's see if it does the same thing when we take matrix A and multiply it by the identity matrix. So we're kind of changing the order of the multiplication here. Well, let's give it a go and see what happens. We're going to do 3 times 1 plus negative 7 times 0. Then we're going to do 3 times 0 plus negative 7 times 1. Then we're going to do 4 times 1 plus 6 times 0. Let's get the right color. There we go. And then lastly, we'll do 4 times 0 plus 6 times 1. Simplifying, let's see what we get here. So once again, looking at our first entry here, the negative 7 times 0 will go away. We get a 3. Looking at our second entry, 3 times 0 will go away. We get negative 7. Third entry, 6 times 0 goes away. We get 4. And last entry, 4 times 0 will go away. We just get 6. And notice once again, the result is the exact same as matrix A itself. So when we have an identity matrix, whether we multiply the identity matrix on the left of the matrix or on the right of the matrix, an identity matrix times another matrix A is always going to be that matrix A. So in summary, let's look at some of these properties that we've found so far. A matrix A plus a 0 matrix equals matrix A. Also a 0 matrix plus matrix A also equals matrix A. A plus its additive inverse will equal a 0 matrix. 0 times a matrix A will equal a 0 matrix. And a matrix A times the proper identity matrix is going to be equal to the identity matrix times matrix A, which is just equal to matrix A. And this is, of course, assuming that matrix A is a square matrix and that I is the appropriate identity matrix. So why do we really care all this much about identity matrices? Well, it turns out they're pretty important for inverse matrices. So when discussing 0 matrices, we saw that adding a matrix A with its opposite or additive inverse would result in a 0 matrix. What about multiplicative inverses? For a matrix A, we will define the multiplicative inverse, a to the negative first power, as the matrix such that A times its inverse will be equal to A inverse times A, which will equal the appropriate identity matrix. And that's great, but how do we find this multiplicative inverse, A inverse? Well, we use something called the determinant. It turns out that every single square matrix has a determinant. And we're going to denote determinant by either saying DET, stands for determinant, so determinant of A, or we can put the matrix name inside these absolute value bars. So the determinant has a formula. We're going to write down this formula here. I'm going to write it in red to make it stand out. But let's say that matrix A has elements A, B, C, and D. Then the determinant of A is going to be A times D minus B times C. I'm going to go ahead and box that because that's going to be a pretty important formula for us. So again, if we have a 2 by 2 matrix, and this is the determinant formula for a 2 by 2 matrix with elements A, B, C, and D, then the determinant of that matrix is A times D minus B times C. Okay, so let's try a quick little practice problem here, and we'll do this one in blue. So let's say that A is the matrix with elements 8, 4, 7, and 6. Let's find the determinant of A. So let's see. We're going to multiply A times D. So multiply the numbers on the main diagonal. That's 8 times 6. Minus, and then we're going to multiply the numbers on the other diagonal. 4 times 7. Simplifying here, 8 times 6 is 48. 4 times 7 is 28. 48 minus 28 is 20. So the determinant of A is 20. Okay, So now that we know how to find determinants, let's figure out how to find inverse matrices. But the first thing to realize is that not every matrix can have an inverse. Only, and I'm going to highlight this, only square matrices with non-zero determinants can have inverses. The reason for this is because when we calculate an inverse matrix, we're going to be calculating with 1 divided by the determinant. And if the determinant is equal to 0, well, we know that we can't divide by 0. So in that case, the matrix wouldn't have an inverse. So for a matrix to have an inverse, we must have a square matrix, and the determinant cannot be 0. Okay? But if we meet those conditions, if we have a non-zero determinant and we have a square matrix, then the inverse matrix, so if A is, and this formula holds for a 2 by 2 matrix, but for a 2 by 2 square matrix A, let's say that A is A, B, C, D, then the inverse of A is going to be 1 divided by the determinant times the matrix where we switch the positions of A and D, and we change the signs of the entries B and C. So let's go ahead and box this formula. We're going to be using this, and let's try an example together. So we have matrix A. Matrix A has elements 2, -3, 4, and 4. And let's try to find A inverse if it exists. Well, to know if it exists, we have to look at the determinant. We got to figure out if the determinant is 0 or not. So let's start there. All right, so determinant of A. Well, we know the determinant is AD minus BC. In this case, that's going to be 2 times 4 minus -3 times 4. Let's see, 2 times 4 is 8, minus -3 times 4 is -12, and then 8 minus -12 is going to be positive 20. So we can see that the determinant of A is not 0, so that means that we're going to have an inverse matrix, okay? Because A is a square matrix and the determinant is non-zero. So let's use our formula to figure out what the inverse would be. And let's pick a little bar here so we have some room to do some work. All right, so the inverse matrix A, or A inverse, is going to be 1 divided by its determinant times the matrix D, A, -B, -C. Let's plug in the pieces where they go. So we know the determinant was 20. We're going to be changing the positions of the numbers on the main diagonal. So instead of 2 being here and 4 being here, we're going to have 4 here and 2 here. And then notice we're going to change the sign of the numbers on the other diagonal. So instead of a -3, we'd have a +3. And instead of a +4, we'll have a -4. And now all we have to do is take this 1 over 20 and distribute it as a scalar. This is going to give us 4 over 20, 3 over 20, -4 over 20, and 2 over 20. Simplifying these fractions, 4 over 20 is 1/5. -4 over 20, -1/5. 3 over 20 cannot simplify, and 2 over 20 is 1/10. Okay, so this is now a really good time to talk about how the Desmos matrix calculator can help us do inverses. So let's hop on over to the matrix inverse calculator, and I'm going to clear all this out. So looking back at our notes, let's go ahead and plug in, let's go ahead and store matrix A. So matrix A had elements 2, -3, 4, and 4. Hit enter. We have matrix A stored. Now there's a couple things that this matrix Desmos calculator can do really well. First off, it can calculate determinants for us. If you see the button down there at the bottom left, it says DET. If I press that, that stands for determinant. We've already stored matrix A, so I'm going to put matrix A right there. And we can see that the determinant of that matrix is 20, just like we got in our notes right here. We got the determinant of A was 20. Okay, so we can double check that with our calculator. Now let's go ahead and calculate the inverse of matrix A. So if I click A, and then I click the button down here right above determinant that has the A to the negative first power, that stands for the inverse. We can see right here, we get the matrix 0.2, 0.15, negative 0.2, and 0.1. By clicking the button next to it that looks like a fraction, we can convert those numbers to fractions. And we get the matrix with elements 1/5, 3/20, negative 1/5, and 1/10. Which, if we jump right over to our calculator, or not our calculator, but our notes rather, that's exactly the answer we got when calculating the inverse by hand. So, the Desmos matrix calculator, a very powerful tool for us when doing these somewhat tedious matrix calculations. What we want to do now is we want to verify for this example that A times its inverse equals A inverse times A equals an identity matrix. Because if we go back to the previous page of the notes, remember, we defined an inverse matrix as a matrix such that A times its inverse is equal to A inverse times A, which is equal to the identity matrix. So we want to verify that if I multiply A right here times its inverse, or if I multiply its inverse times A, that in both cases, I'm going to get the identity matrix. Let's use Desmos to check this. So we already have matrix A stored. Let's create a new matrix. Actually, we don't even need to do that. Here, let's click on a new line here. And let's just go ahead and let's try it out. Let's do A times A inverse. Notice we're getting 1, 0, 0, 1, the identity matrix. And then now let's calculate A inverse times A. And again, notice we get 1, 0, 0, 1. What this is showing here is that, first off, our inverse matrix is correct. And that A inverse truly is A's inverse, because multiplying it times A, or multiplying A inverse times A, or A times A inverse, in both cases we get the identity matrix. Now what I did here on the notes is, or at least the notes that you'll see online, I went ahead and worked it all out by hand, but we're just going to say, we checked it in Desmos, we saw that A times A inverse gave us the 2 by 2 identity matrix. We also saw that A inverse times A gave us the 2 by 2 identity matrix. And we'll call it a day there, verifying that A inverse truly is the inverse of A in this case.